Okay, so last week we started with the simple linear regression model. Okay, so we continue from there today. Last week we were able to derive the formula for finding the values of the parameters, the A and the B. After finding the parameters, we were able to find the regression equation or the regression model. So today we'll look at how to partition the total sum of squares into regression sum of square and then error sum of square. Last week, this is the linear regression model that we used, y equals a plus bx plus e. So any linear regression model is made up of two parts, the linear function part, the a plus bx, and then the residual part as our e. So whenever you have the actual value of y, we can always decompose the value of y uh, into two components, one coming from the regression part, that is the linear function part, and then the other coming from the residual or the error part. This is what we had from last week, that y prime is equal to this. This was the value of a, this was the value of b. So if you want to find the estimated value of y given x, you just substitute the value of x here, and that should give you your y prime. Okay, so we'll use y prime to stand for the estimated y, and then when you see y, that is the actual y, the y that was observed. Okay. So for example, if you go to the table, okay, if you go to the table and you pick x is equal to 61, if you pick x is equal to 61 and you substitute this into the regression model, you get y prime to be 108.19. Okay, 108.19. But as we said last week, there's always a difference between the actual value of y and then the estimated value of y, what we call the error term or the residual. So when you go to the table, you find the actual value of y when x is equal to 61. That was given as 105. So the actual y is 105. But then from our regression model, our estimated y is what? Is 108.19. 108.19. So it means that if you want to find the residual part, it's just going to be the actual y, which is 105 minus what? 108.19. Okay, that is going to give you the error or the difference between the actual value of y and then the how do you call it, the estimated value of y. So if you are asked to find a residual, you have to do it for all the observations. You go to the table, you do it for, I think we had like 10 observations. So you do it for all the observations. When you pick the value of x, you go and put it into the regression model, find the estimated y, then you just find the difference between the actual and the estimated. So let's look at this table. Last week, this is the table that we used. This was the price. So x was price and then quantity was y. Now, if you want to find your y prime when x is equal to 61, put the 61 into the regression model. That will give you your y prime. Okay, that will give you your y prime. So we are getting 108.19. So to find the residual, we subtract the estimated y from the actual y. So we'll have 105 minus 108.19. That is giving us minus 3.19. So you have to do it for all the levels. Okay, do it from 1 to 10. So you do all this. When you find the sum, okay, if you find the sum of this, you'll be getting 0. That is why the mean, if you remember, it was part of the assumptions that the estimated value, the expected value of the error term is 0. We said there are positive sides and there are negative sides. So the positives will just cancel the negatives. So on the average, we'll get an error of 0. So that is what we have here. Okay, so just find out the residual terms, sum them up. When you find the mean, it's going to be the summation over n is 10, and we'll be getting 0. Okay, and one of the assumptions too was that the expected value of the actual y is equal to the expected value of the linear term. The linear term is the estimated y. So if you compare the means, this is the mean for the actual y, this is the mean for the estimated y. You see that they are the same. Okay, they are supposed to be the same. And then if you look at the variance, that's the dispersion of the actual values of y from the mean. Okay, that one too will be the sum of the variations or the variance in the estimated y and then the variance of the error term. So this is what we will be trying to prove, that if you want the variance in the actual value of y is equal to the variance of the estimated y, the one from the regression, and then the variance of the error term. So that is what we'll be trying to do today. But then this is how we find the residual term. Okay, so now when you take your y, okay, if you take your actual y, it's going to be the sum of the estimated y and then the residual term. This is the residual term. Y minus y prime is the residual term. So when you add the residual term to the estimated y, then you're able to get your actual y. Let's look at this from the table. If you add this, if you add the y prime to the residual, you get your actual value of y. Okay, you have to get your actual value of y. So just like the variation to, if you want the variation in y, if you want the variation in the actual y, it's supposed to be equal to the variation in the estimated y and then the variation in the error term. Okay, so when you add the two variances for the estimated y and then the error term, we're supposed to get the variance in the actual y. Okay, so we'll try and decompose the variance of y into the two components, the variance of y prime and then the variance of the error term. This is just the graphical representation. Let's use the mass to show that. Now, if you take a point like 65, 120 from the table, okay, x was 65 and then y was 120. Okay, we want to first find the deviation of the actual value of y from the mean of y. From last week, we saw that the mean of y was 150. And then if you pick this point, the actual value of y is 120. So this deviation is going to be 120 minus the mean. Y minus mean is the variation in y, or the deviation of the actual value of y from the mean of y. So we have 120 minus 150 is giving us minus 30. Okay, minus 30. So this is the variation in y for that observation, or the deviation of this observation from the mean. And what you are trying to say is that this deviation here can be decomposed into two. One is from the linear side, that is the one from the regression side, and then the error part. Okay, this minus this deviation of minus 30 that we have in y, some will be coming from the deviation in the estimated value of y and the error part. It's all be because when you add the error to the estimated y, then you get your y. So if you are finding the deviation in y, then it should be the sum of a deviation in the regression and then the difference from the error part. So let's try and see if we'll be able to decompose this minus 30 into the linear and then the error part. If you want to find the deviation from the linear part, you subtract the mean from the estimated value of y. You see how we found the deviation of y from the mean? It's y minus the mean of y. So the one from the linear part should be y prime, that is the estimated y, minus the mean of y. So what we have to do is that we need to put this x into the regression model to find our estimated y. Okay, put 65 into the regression model to find your estimated y. So when you do that, x is 65, put it here. You're getting 136.19. So y prime is equal to 136.19 when x is equal to 65. So now, if you want to find the deviation from the linear part, that's the deviation due to the regression model, that is y prime minus the mean of y. Okay, so this is the deviation which is coming from the regression model. So you subtract the mean, which is 150, from the estimated y, which is 136. Okay, so we are getting minus 13.81. So out of the minus 30, minus 13.81 is coming from the linear side. Okay, it's coming from the linear side or the regression side. Then let's look at the one from the error part. For you to find the error, you subtract the estimated y from the actual y. So y minus y prime. The actual value of y was 120, and that of y prime is 136.19. Sorry. When you find the difference, we are getting minus 16.19. So when you add minus 16.19 to minus 13.81, you get minus 30. Okay, you get minus 30. So what you are trying to say is that if you find the deviation of y, the actual y from its mean, it should be equal to the deviation of the estimated y from the mean of y. Then you add the error part, which is actual y minus the estimated y. Okay, so when you add these two, you should get exactly y minus the mean of y, which is the deviation of the actual y from this mean. I hope we understand.
Hello, sir.
Yes.
Please, I understand the calculations and everything, but I don't understand the parts, like adding everything together. When you said when we add the linear deviation and the error deviation, we are supposed to get something. Can you please go over that part?
Yeah, it's from here. Okay. What we are trying to say is that when you decompose the deviation of y from its mean, okay, if you find a difference between the actual y and then its mean, we can decompose it into one, the deviation from the regression model. If you want to find a deviation from the regression model, you subtract the mean from the estimated y, and then the residual part. What we are trying to say is that when you find the deviation of the mean of y from the estimated mean and estimated y, and then you add it to the difference between the actual y and the estimated y, you are supposed to get the deviation. Let's take this. You will see how it works mathematically. Look at this. Okay, look at this. Are you following? Y minus the mean of y, we are saying is equal to y prime minus the mean. This is the deviation from the regression model.
Yes, yeah, I'm following.
This is the deviation from the regression model, and then this is the error part. When you expand this, okay, you get y prime minus mean plus y minus what? Y prime. You see that the y prime will take this y prime away. Then we'll be left with y minus the mean of y. You see that it's the same as this. Are we together? Hello?
Yes, sir.
So whenever you add the deviation of the estimated y from the mean and then the error part, you are supposed to get, yes. You are supposed to get this, okay? But even we derive this formula from this. If you want the actual value of y, okay, is equal to the sum of the mean, then the deviation from the mean due to the regression model. That one is the y prime minus y. And then the error part. Okay, y should be equal to the sum of this whole thing. Let's go to the table and verify that. Now, the actual value of y here is 105. Okay, 105. Now, we are saying that if you want to get your 105, you add your mean, you add y prime minus the mean, and then you add the residual term. So let's try that. Please, if you have a calculator there, let's see if 105 will be equal to the mean is what? 150, right? The mean is,
Yes.
Is it 150? 150, right? 150.
It's 150.
Then we add y prime minus the mean. So 150 add 108.19 minus 150. Then you add the residual. And let's see what we get. First, you add the mean. So the mean is 150.
So is that 108.19 minus 1?
Yes, minus
Okay.
the mean, minus 150. Then add the residual. What did you get?
So I got something like 45.
No. It can't be 45. Is the mean is what? The mean is 150, right?
150. Yes.
150. Then you add y prime, which is 108. This one, add this, okay? And that one too, we are talking about the deviation. So it's y prime minus the mean again. The mean is 150. Okay, 150. And add the residual. So is she the only one with the calculator?
Sir.
Yes, I mean.
Yeah, I did it. So I got 105 point something, but then I saw your explanation. I don't know if I did it right. I added the mean to the y prime, to the difference between the y prime and then the mean.
And the mean.
And then I added the residual number. Yes.
This one is minus, so it has to be minus this.
Yes, so you get 105.
It's supposed to be exactly 105 because this point here will take this point away. You see, this is minus 0.19. This is positive 0.19. So it will take it away. So when you add all the components, you are supposed to get the actual value of y. Is that okay?
Yes, sir.
Yes.
All right. So from here, this is the equation that we have now. Okay, this is the equation that we have now. We are trying to find the variance in y. The variance in y, that is the variability in the dependent variable, the actual value of y. And I'm sure you all know how to find the variance of group data. It's first you find the difference between the observations and the mean. You square them, you sum it up, then you divide it by the number of observations. So if you want to find the variance of y, it's sigma y minus y, the mean of y, all squared, divided by n. Okay, divided by n. That's how we find the variance of group data. So now from here, we just square both sides and then we sum them up. We are doing that because we want to find the variance, okay? Just because we want to find the variance. So by squaring both sides and summing them, the left-hand side becomes sigma y minus the mean of y squared equals, we are squaring this whole side, okay? So group it square it, and then you find the sigma. Then your next step is to expand the right-hand side. You need to expand this. Okay, so I'm sure you remember binomial theorem. If you have a plus b all squared, it becomes a plus 2ab plus b squared. Okay, so when you expand this, we'll have the left-hand side is still sigma y minus y prime squared. Then the first term is going to be sigma y prime minus the mean of y squared. The last part will be y minus y prime squared. This term in the middle here is going to be 0 because y minus the mean of y prime is 0. Y minus y prime is 0. If you sum up y minus y prime, it's going to be 0. We said that the summation of the error term is always 0, and y minus y prime here is the error term. If you subtract the estimated y from the actual y, that is the residual. When you sum them up, as we said, some are positive, some are negative, so they will just cancel each other out. So the term in the middle here is going to be 0. So if we eliminate this term, then we'll be left with this. We'll be left with this. Forget about the n first. So we'll have sigma y minus the mean of y squared is equal to sigma y prime minus the mean of y squared plus sigma y minus y prime all squared. We call this the total sum of squares. Total sum of squares without the n, okay? We call this the total sum of squares. We call this the regression sum of squares, and we call this the error sum of squares. So in case in a question you are asked to find TSS, if you want to find TSS, just find sigma y minus the mean of y squared. The value that you get there is your TSS, the total sum of squares. So first you need the mean of y, then you find the difference between the mean of y and all the observations, square them, find their sum. That is your TSS. If you want RSS, regression sum of squares, you find your estimated y. So first you need your regression model, find all the various estimated values of y, then you subtract them from the mean of y, square them, and then sum them up. That will give you a TSS. And then the RSS, the residual, or here we call it the error sum of squares. This one is ESS. And that one is after finding the error for each observation, just square them and then you sum them up. If you square them and you sum them up, that one you are not getting 0, because even if you square a negative number, it still becomes positive. So that is how we find the TSS, RSS, and then the ESS. So what this means is that the TSS is equal to the summation of the RSS and then the ESS. If you add regression sum of squares to error sum of squares, you get your total sum of squares. But then now, if you divide through by n, then you are getting the variance. So the variance of y should be equal to the variance of the regression, the one from the linear part, and then the variance of the error term. Okay, so variance of actual y can be decomposed into two, one from the linear side and then the other from the error side. Okay, the other from the error side. When we divide through by sigma y minus mean squared, then what we are getting is this part here is going to be 1. So what it means is that the sum of the ratios of the RSS and the ESS to the TSS is supposed to give us 1. I just said that this expression here is called the TSS. This is the RSS. So what we have here is RSS over TSS. Then this is ESS. So we have ESS over TSS. So the summation of the ratio of RSS to TSS and ESS to TSS will give us 1, since TSS over TSS will be 1. Okay, will be 1. We will use this when we are finding the coefficient of determination. So let's keep this in mind. So just in case you are asked to find, what they normally ask is the TSS, RSS, and then the ESS. But in case you are supposed to find the variance, you just divide it by n. That's the number of observations. Then you are able to get your variance. All right. Let's look at an example. We are using the example we used last week. So the price was X and then quantity supply was Y. Okay, quantity supply was Y. So let's see how we'll be able to get TSS, RSS, and then ESS. Now, you pick the values of Y, the observations for Y. We know the mean of Y is 150. Okay, so we have our 150 here. So if you want to find your TSS, it's sigma Y minus the mean of Y squared, which means that first we have to find Y minus the mean of Y minus the mean of Y. So this is giving us 105 minus 150, it will be minus 45. 120 minus 150 will give us minus 30. So you do it for all the observations, okay? When you are done, you square them. We have Y minus Y, the mean of Y squared. So square all the Y minus the mean of Y. Square all of them. And then when you sum them up, this is your TSS. Okay, your total sum of squares. This is your TSS. Are we together?
Yes, sir.
Okay.
Yeah.
Then let's move on to the RSS. You need to find your estimated values of Y. So that one, you take your X, you go and put it in the regression equation. So pick all the observations of X.
Sir. Yes, sir.
Take all the observations of X and put them into the regression equation to find your Y prime. After finding your Y prime, we need Y prime minus the mean of Y. So you subtract 150 from the Y prime for all the observations. After finding Y prime minus the mean of Y, we need the square. So Y prime minus the mean of Y squared. So you square all these values. After doing that, when you find the sum, that gives you your RSS, the regression sum of square. Then let's go to the error part. That one is Y minus the mean of Y. So Y minus Y bar. So Y minus Y bar. So 105 minus 108.19. You get your answer. You do it for all the observations. Then you square them. After squaring them, you find their sum. This is going to be the sum. Okay, so this is your ESS, error sum of squares. So if you add the error sum of squares to the regression sum of squares, you'll be getting something around the total sum of squares. Because of decimals, it's possible it might be more or fall short by just some few decimals. Okay, I hope we understand. So if you want to find your variance, these values here, I think they are wrong because the variance of Y is the TSS over N. TSS over N. But look at what they are getting here. I don't know if they are using N minus 1. Let me see. Yes, I think they are using the formula sigma Y minus the mean of Y squared over N minus 1. I think if the sample size is less than 0, they use N minus 1 or something. Please, do you remember something like that? Is there any star student here? But you all did echo stars. Didn't you do variance in echo stars?
Yeah, so we did.
I think the variance formula is either we use the sample size or I think one is the sigma 10 over N minus 1. I think that's what they use there. If you use N minus 1, then we are getting 1155.555.6. So now if you add the variance from the regression side to the variance of the error term, then you get the variance of y. Okay, you get the variance of y. These things,
Sir,
yes. Yeah, Kwame.
so can you please come again? You said when do we use the n minus one? Can you
I
please come
don't.
again? You said
I
when do
am.
we use the
I am. I am not very certain about that. But you can just verify it.
okay?
Let me see. Let me just verify. Yes. They use think let me see the variance for group data for sample. Yes, for sample, because a sample they use they divide it by n minus 1. You see, for the population variance, that is why they divide it by n. But because this one is a sample, it's just 10 observations out of many. So they divide it by n minus 1. Okay, n minus 1. So if it's sample, we divide it by n minus 1. Okay. Now, these things, if you are doing these things under pressure, if you don't take your time, you just be making mistakes. So please, you have to practice them and make sure you have control over it. All right. If you remember the ratio side, we said that RSS over TSS plus ESS over TSS should give us 1. You can verify that one too. This is RSS, this is ESS. If you divide it by TSS and you add them, you are getting 1. Okay. You are getting exactly 1. So that's it. Please try this one. Last week I told you to try something and send it to me. No one did. So try this one. Find the regression of y.
Yeah, we didn't know we were supposed to send.
But or maybe I said if you had an issue, then you let me know. But because you didn't let me know anything, I was happy because you were able to do everything. So please try this one. Find the regression of y on x, then find TSS, ESS, and RSS. Then prove this, okay? That the proportion of ESS and the RSS to TSS. If you add them, you have to get 1, okay? So try them. I'm sure you can do that. Okay. The next thing is about the coefficient of determination. Last week we said we're using the least squares method, and it tries to reduce the value of the residual term. If you have a regression model, okay, you are trying to use it to predict the value of a variable, but then that variable too has its own actual value. Okay, that is why there's always an error term. But if you are able to reduce that residual term to the lowest term possible, then it means that your model is more efficient. So the least squares model is able to reduce the error term, but it cannot eliminate it altogether, which means that definitely there will still be some difference between the estimated value and then the actual value, which means that whenever there are changes in the dependent variable, all of these changes cannot be explained by the independent variable. Let me use the wage example. If we have a simple linear regression model of wage on the workers' educational background, this is a simple linear regression model. So we want to know how the changes or the variations in the workers' wage can be explained by their educational background. But because of the residual term in the regression model, we cannot say that variations in the workers' wage can only be explained by the person's educational background. It's possible other factors can also explain the changes in the wage. I hope you understand